any of these ciphertext bits get hit by the error on the wire, on the wireless or whatever on the way to the destination, then the errors will propagate to all the future blocks. Okay, so that's the disadvantage of most of these actually thing is that you are propagating. Then if one block error will basically cause problems until you resynchronize, start the IV again, and do it. Okay, so this is again this is the second mode of operation, CFB. Or actually, this is the same thing. Hold on, we have to go move back to the previous one. Output feedback. In this case, rather than taking the ciphertext to the next block, we take the output of the encryptor to the next block. So this is very similar to the previous one. We take what we call nonce. What is a nonce? Nonce is basically once, it is used just once. So it is not used more than once. And so we take a number, a random number, which we use just once. And so we encrypt it with the key, and the output of the key is sent to the next block where the key is again encrypted. Where the output is encrypted with the key again, and to the next block and to the next block. And underneath here, we take the output of the encryptor and exclusive OR with the plain text, and so we get the ciphertext. So basically, this is slightly different from the very first method that we had seen, where we had ciphertext chaining, is cipher block chaining, CBC. In that you see the whole thing which is in the dotted line can be pre-computed. So you don't have to do it online. You could just take the key and take the nonce, and then you can compute all the blocks beforehand, and when you get the plain text, you can exclusive OR with that output, and you get the ciphertext. Okay. So this allows parallelism in that sense that you can do the encryption later, or as opposed to in the cipher block chaining, where you got the encrypted text, and then only when you got the first plain text and you got the encrypted text on the plain text, then you can use it on the next plain text. And so you really couldn't do P2 before P1. Here you can do P2 before P1, or you can do P2 in parallel with P1. So OFB, the output feedback, the main thing is that you need a initialization vector which is unique for each case, because if you use the same initialization vector, you will get the same output blocks, and therefore the attacker can reuse that. Basically, it can take the ciphertext and then exclusive OR with the same IV, it already knows the output, and get back. So very easy, right? So you do not want to use that IV any time again. And that's why it is called nonce. Bit errors do not propagate. Another advantage is that if you get one bit error in any block after transmission, that will affect only that block. Because we don't use the ciphertext and C2 or CN or anything for the next block, right? More vulnerable to message stream modification. So basically, since it is simply an exclusive OR with a pre-computed stream, somebody can easily play with the ciphertext, change it, and then you might get a different plain text at the receiving end. So you have to be careful about, when you get a text, you need some other methods to make sure that none of this was changed. And the sender and receiver must remain in sync So that's another thing, is that if any of the blocks are lost, then obviously none of these methods will work. So we use only use with the full block feedback. Subsequent research has shown that only full block feedback should ever be used. So rather than, even though it is called a stream, so unlike the previous one, you cannot use 1 bit, 4 bit, and those could cause problems, and therefore only full blocks are recommended for this method. Okay, output feedback. Okay, one of the most common method is the counter method. In the counter method, basically rather than feeding back from one stage to the next stage, we take counters which are incremented every time, and the counter is encrypted, then it is exclusive OR with the plain text, and you get the cipher text. So now you can see that depending upon the value of the counter, the same plain text will result in different cipher text. Okay, and you have the advantage of parallelism. You have the advantages of other things like pre-computation and so on. So basically what you want to do is you want to have counters which are not reused, because if you reuse the counter, then it's the same encryption value that will come, and one can easily compute backwards. So CTR is actually one of the most common method which is used, as you will see later on, and it can be done, we already said it can be done in parallel, can be pre-processed, and it is good for bursty high-speed links where you want to produce the cipher text at a very high speed. Random access to encrypted data blocks, and then second thing is that you could go to the block P2 before block P1 or block Pn before P1, and just imagine if these are not the blocks which are being transmitted on the wire, but these are being stored on the disk, encrypted blocks which are stored on the disk, you can read any block and decrypt it. Right? Provable security, and so people have theoretically proven that this works very good. And main thing is that you do not want to use the same key at the same counter value, because if you use the same key at the same counter value, you will get the same encrypted value, and the attacker will be able to find plain text very easy. Let's see, any questions about any of these modes? Yeah, go ahead. Yeah, the question is, since there are n counters, how do you pass on the n counters? Initial vector was easy to pass on with one counter. How do you pass on n counters? Is that the question, right? Yeah. So basically, the counters would have some kind of algorithm where you can compute. I mean, you can basically, only thing we care about is the initial values of these counters, and you could pass on all n. You could basically have some algorithm so that you could calculate the counters from one counter, and so it will basically be as strong as the initial value IV. Okay. So yeah, and that's the answer. Any other question? So now we are going to talk about storage encryption. So the encryption is used not just for networking but also for storage. Everything that is stored on the disk, needs to be encrypted if you want to keep it secret. And so basically, the same techniques that we have talked so far work here as well. Few things that we need to know are, for example, if you are going to do encrypt a file, then for each file you need a different key, because if you use the same key for several files, then if they basically, they can use, that just gives them more data for the same key. I mean, remember we talked about that we don't want to have the attacker more than one sample for a given key. And so, and this will be repeated actually throughout this class, that you want to use the key minimum number of times. So for each file, we'll use a different key. And then you might be able to protect the data, but not protect the metadata. Metadata is things like which go in the file headers, which we don't generally see in the data itself, such as file name, creation date, modified, last modified. Those things may be may remain in clear, because you want to be able to back up and things like that. So, for example, if you encrypt all that, then the backup program will need to have all these keys to be able to decide which files are new, which files are old. And so some of you use encrypted file systems, which is provided by NTFS in Windows. That uses this kind of information. Basically, it encrypts each file with a different key, and then the metadata is not encrypted. You can also do disk encryption, where whole disk is encrypted, every sector on the disk is encrypted, and so you could use either single key or multiple keys for the same disk. Basically, you could have different partition, as we call them, on the disk. Each partition could have its separate key. Now, in this case, just like the metadata in the file is not encrypted, the master boot record may or may not be encrypted. Boot partition may or may not be encrypted, because anybody, I mean, not anybody, at least when you want to boot at that time, you may or may not have the key. But it is possible to encrypt the boot record, and in that case, when you boot, it will ask you for the password right there at boot time. And so the second precaution we have to take is that what is kept in the memory. Because if you keep the keys in the memory, then somebody can write a program that does some kind of buffer overflow and can somehow read unauthorized parts of the memory and may be able to get hold of some of these keys. So basically, we don't want to store too many keys in the memory. Now, new computers nowadays come with TPM. TPM is the Trusted Platform Module. And so there is a secure coprocessor chip on the motherboard that can authenticate a device. So basically, on your motherboard, there is a processor and there is a TPM module. And so that module cannot be broken in by anybody. And that actually allows that whenever you get a new device, whenever you put any device, such as a disk or something like that, it can figure it out that this is the original disk or not. And then, so the disk can only be read on that system. If you take the disk to some other system, it will not let you read it. Okay? So if the disk becomes bad, then you need to supply the password, and then it can probably be recovered parts of it. Okay? I don't know how many of you have heard of something called TrueCrypt. TrueCrypt. How many of you have heard TrueCrypt? Raise your hands. Nobody has heard TrueCrypt? So just Google it next time. T-R-U-E, True, C-R-Y-P-T, Crypt. One word. I use that, actually. That's a very powerful encryption system. And so I use that to encrypt my disk. If you need any privacy or if you have any security concerns, you might want to look into that. It's free, open, basically. I wouldn't say that it is open source because the developers have the code and we don't know what the code is. And so that is one of the concerns people have. But in practice, there are lots of stories about how a lot of people, saved themselves from trouble by using encrypted file system, using TrueCrypt. So in the storage, you could use cipher block chaining, as shown here. You take the ciphertext, give it to the next block, and so on. And so main thing here is that the ID cannot be predictable, and because everybody can read the ciphertext, they can read all the blocks very easily on the disk. They can take the disk to any computer and read all the cipher blocks. And so if they know IV, then it becomes kind of easy to discover things. So here's the thing. For example, if you have two messages whose first blocks are some bit pattern B, exclusive OR with IV1, and you have another block message which has B with exclusive OR with IV2, when you take it through the encryption, IV1 encrypted and IV2 encrypted, when you exclusive OR them, the first blocks actually will come out the same, because once you know the IV, and the C1 in the first message and C1 in the second message would come out the same. Okay, so basically you don't want to disclose IVs, and the main thing is that you don't want serial thing. For example, if you do CBC, then to encrypt second block, to decrypt second block, you need to decrypt the first block, and that is not really a good idea, right? So instead of this CBC, you might use the other technique, which is the counter mode or OFB, one of those which can be done in parallel, right? This is about storage encryption. XTS AES mode. XTS stands for XEX based tweaked codebook mode with ciphertext stealing. So we already know what is ciphertext stealing. We need to know what XEX is and what is tweaked codebook mode. XEX stands for exclusive OR, encrypt, and exclusive OR. Okay, and we will see that process in a minute. And so you create a unique IV for each block using AES and 2 keys. Yeah. So as it says here, we create a unique IV. We create a unique IV for each block using AES and 2 keys. Okay. So for example, so what we do is we get a value T. First we have a counter I, and that counter is encrypted with a key. If you look at the picture below, you see that the counter I is encrypted with key 2. Look at the picture below. And it is exclusive OR with alpha raised to j. Alright? Now this is mathematical in the sense that alpha is a polynomial. Okay? And it is raised, alpha raised to j is done in Galois field 2 raised to 128. Okay, we saw the examples of 2 raised to 8 Galois field in our previous chapter. Here it is 2 raised to 128. Okay, so the power of the polynomial could be all the way up to 2 raised to 127 or so. Okay, 0 through 2 raised to 127. So that big polynomial is alpha. and then you do alpha raised to j for the jth block, and ith is the jth is block number, and ith is the sector number. Each sector has n blocks. So basically on the disk, each sector might be, let's say, 512 bytes or maybe larger, depending upon what sector size you selected. And your block size will depend upon what encryption key size you use. So you could have more than one block in each sector. So for each sector, for the ith sector, j is the block number, and the I is used with key 2, then exclusive OR with alpha raised to j. That gives you tj. And as you can see in the picture below, plain text j, tj, is exclusive OR with tj, and then encrypted, and then again basically this exclusive OR with tj to get cj. Alright, the cipher text j. So what this allows is that everything can be read in parallel. You can see that if you know I and j, and if you know key 1 and 2, then you can just create tj and you can go backwards from cj to pj. Right? Now on the right side at the bottom, we see a picture of how the last block is handled. Last block is handled with cycle stealing. Cycle stealing, we already talked about how it is done. Basically, you take the last one block and take some cipher text from there and combine with the plain text of the last block, encrypt that, send it over first, and so on and so forth. So the same process that we saw before for cycle stealing is done for the last block here. Okay? So this is a standard XTS AES mode. AES is the encryption technique, and XTS is this whole thing about exclusive OR, encrypt exclusive OR. You can see that PJ is exclusive OR with TJ, then encrypted, and then exclusive OR again with TJ. Okay, so that is the XCX based technique, and codebook is tweaked. The tweaked means that this whole business of taking a key 2 and then encrypting it, encrypting I with key 2 and then exclusive ORing with alpha j, all that process is the tweaking process. So that way, for the same plain text, you won't get the same cipher text, even though the key is same. Okay, so this is basically this is a standard which has been developed for this purpose. Okay, let's see advantages and disadvantages of this before we can take more questions. So here is the polynomial. X raised to 128, I said 127. So basically G of 128, G of 8 was X raised to 8. So this is X128 for G of 128 plus X7 plus X2 plus X plus 1. And this would be a prime polynomial. It is very difficult for us to just prove very simply that this is a prime, but one can do the calculation and figure it out that there are no factors of this. This is a prime polynomial. And then the efficiency is that you can do parallel encryptions in hardware or software. You can do random access. It has both nonce and the counters. And it is defined in IEEE standard 1619 for block-oriented storage use. So basically this is used for disk storage. And it is used in many packages, including TrueCrypt. So this is the name I was mentioning before, TrueCrypt. This is the package that I use, and right now, if you go to download it, it will say that they have stopped supplying it. Actually, they recommend that now you use Microsoft. I think something happened between these people who developed TrueCrypt and Microsoft, that now they are not giving TrueCrypt anymore. So you have to really find an older version of TrueCrypt and use it, and people are still doing it. So I don't know about that. But anyway, FreeBSD, OpenBSD, those are the operating systems. And those operating systems use this software, and they use this technique. Even Mac OS X File Vault uses the same thing, and many others as listed here. So that brings us to the end of this module, which is 621. I'm on slide 621. Summary. And the summary of this is basically in pictorial mode. We first in this chapter we talked about 3DES, and 3DES, triple DES actually uses EDE. The reason we use EDE is so that if you have the same key, you get single DES. And D is as good an encryptor as E, so decryption and encryption are really equally powerful. Second thing we do is we just use only 2 keys, because regardless of how many keys you use, even if you were to use 3 keys, you will get only 112 bits of protection because of that middle attack that we saw. So only 2 keys are used. Then we talked about how to ensure that the same plain text does not result in the same ciphertext, and for which there are many operating modes. If you don't use any of the operating mode, that is called electronic codebook, ECB. Electronic codebook is not used, because if you use electronic codebook, basically every block which has the same value will result in the same output, which is not good. So we use, first thing we start with cipher block chaining. In cipher block chaining, we take the whole ciphertext and exclusive out with the next block. And the problem with that was that you could not do it in parallel. Everything is sequential. So we talked about cipher feedback mode, where actually cipher feedback mode also has the same problem, that you could not do in parallel, because the plain text output and the ciphertext output is used as the input. But what is good in this one is that you can do it in some parts. In you can. The second one is output feedback mode, in which you can do it in parallel. Basically, the plain text does not come in until the last minute over there. You see the bottom, the figure C. And so the feedback happens before that, so you can do all the computation beforehand. So output feedback is one. And then the counter mode has similar properties, and I think counter mode is probably the most used of all these modes. And then we saw the XTS AES standard, which is which has all the good properties of pre-computation and everything. And the main thing is that this is good for storage, because you can do random access. You can take any block, encrypt it, and decrypt it without having to decrypt all the blocks before it. Okay, so these are all different modes. That's all on this slide. Any questions on this slide? That's the homework. And the homework is that for each of the modes, ECB, CBC, and CTR, electronic codebook, cipher block chaining, and for the counter mode, identify whether decrypted plain text block P3 will be corrupted if there is an error in the block C1 of the transmitted ciphertext. So basically, you have to figure out in each of these 3 if the errors propagate. And then part B, assuming that the ciphertext contains n blocks and that there was a bit error in the source version of P1, identify how many ciphertext block will be propagated. So now here the error is not in the ciphertext, error is in the plain text. So before you encrypted, the plain text was in error. Okay, so the question is how many bits that error will affect in the next few blocks. All right. So think about it. Basically, when you read ECB, CBC, and CTR, you should be able to basically come up with the answer for this. slide numbers. So we move on to 623. So in this lab homework 6, what we want to show you is that why you should encrypt your communication. And so basically all we do is you need two computers, and basically you can do it on our computers, the client and the server. Now you have the password on both. So you can telnet first. Telnet does not encrypt. And then you use Wireshark to see what is going on the wire, and you log in and you can see your password in clear, and then you have to circle that. Then you do SSH, which is encrypted, and then you do the Wireshark and see if you can find your password. You won't. And this is interesting because I remember 10 years ago, or 10 or 15 years ago, I went to a conference when the wireless was very new. So they gave us free wireless cards. Anybody who needs a wireless, that time computers didn't come with a wireless built in. We had to use a USB plug-in for wireless, for Wi-Fi. So they gave us free Wi-Fi USBs so you can connect. And then in the evening, in the dinner meeting, they presented everybody's password, because it was so easy to just watch the, so it was easy to just use Wireshark to see what is going on. And all you have to do is, after the word password, PASSWRD, whatever comes is actually your password. And so it's very easy to catch on if it is not encrypted. And so this exercise does exactly the same thing. And from after doing this exercise, you hopefully will not do any more telnets, because anybody else can see it.